Okay, READiStrength project. The subtitle tells the aim and also what it is about. Resource efficient, data-driven, integrated log and board strength grading.
So the background for this project is the need for raw material efficiency. We have an increasing use of wood in the building industry, and we want this to increase even more, to exchange concrete constructions to wood constructions. But we also have a limited amount of wood, and that means that we have to use the wood as efficient as possible, of course. The problem when we want to utilize wood in an efficient way is that wood is, as you know, a biological material. That is, we have a huge variation of properties. Every log, every tree is unique, and thereby we have to find the best way of utilizing every single log. But today, the fact is that we are actually not using wood to its full potential. Most construction wood is sold as a strength for 24 megapascal, C24. That means that when we use the wood, we design as the wood having a strength of 24 megapascal. But if we look at the random boards, so the strength distribution of random boards from Norra Timber Säva sawmill, as an example of a typical sawmill in Sweden, we can see that we have the average strength is about twice that strength, around between 45 and 50 megapascal. And that means that we are actually not using wood at all to its full potential. And if we want to use wood more efficiently, then we need to define the strength better.
If we then go further into technology, so that is the most advanced technology that we were able to use, and there are about 10 to 12 installations worldwide of that technology, and so we are lucky to have one here in a sawmill, and in Freiburg we used, say, a prototype which is actually the basis, or a little bit of the basis of these industrial installations. So the difference to the to other X-ray based technology is that we have an X-ray source which actually travels around the object while the log is moving, and the result from that is not only one or two planes which we are looking at, but we are able to look at several hundreds individual planes, which are then recalculated to a proper 3D representation of the log internal structure, as you can see here in the cross-section or in the axial length. And from this, again, we can extract, again, all the external data. We can extract the wood density level in much more detail, as I've shown in the image before that. So we can find the actual precise position of knot structures. We have information on the status of knots. So the detailness of information is higher than with the previous X-ray based technology.
So this is what we envision in a perfect scenario here. We have a sawmill process, very simplified. The log comes in, we scan it, we saw it, we dry it, and so on, and then we do some grading. And nowadays, this grading is based on pretty much statistical models, statistical correlations to predict certain mechanical properties. My vision is to use the plentiful data we gather in these X-ray CT scans, add some computational mechanics to it, and produce numerical models that could predict certain properties of the planks to improve our grading and maybe one day even say a target use for that specific plank we're looking at.
But if we're able to choose the perfectly choose the high strength logs, we can find these logs, which is 40% of the total amount of logs, We strength grade those logs and are able to cut dimension A. And then we will produce only high strength value for these. So we get 40% instead of 20% of the total material as high strength, high value material. And the rest of the material, 60%, is cut to dimension B, where we produce 48% of the total flow will become standard instead of 40 as before, and 10% is the normal reject in dimension B. In a total, this will give a much higher value with no of the lowest value, the reject with dimension A, and a high amount of high strength lumber in dimension A, giving us a much better value, much better utilization of the logs.
Just to let you know, again, have in mind that is a pilot study, and altogether we used 420 logs. We're about 1,200 boards, which is overall for 4 species a very small number.
It is very important that the quality related to or the quality which is included in the data, this has to flow upwards and backwards, which means we have to fulfill the need and developing solutions on the point that from the forest stand, the data information can flow before felling already to the sawmill, and after processing a log or several logs, we have to make clear that this information can also flow backwards, that this information can be used from the forest owner side.
Mm-hmm. And the idea was if we can feed forward the information from the log side, when we do the prediction on the board side, can we improve it? That's the question. And it turns out that we probably can. This is one example for Norway spruce.
A pre-graded source is just another source in the same way as a new geographical source. And then there are, in the standard, there are very precisely described the procedure to do it. So it would be quite easy.
Our project READiStrength was a lot of testing and a lot of modeling, and what we can say is we wanted to predict strength, board strength based on log scanning, and yeah, that's something that works. We can really do that. It absolutely makes sense. Obviously, it works best with the best data, so that's log CT scanning, but it also works quite well with X-ray scanning. You can even squeeze out some information from 3D scanning, from outer shape scanning, but as you saw, the correlations are a bit shaky. Thanks to the explanations of Rune, we can also say currently the standardization does support log strength grading, log pre-grading, if you know how to do it, if you do it correctly. So it's we can actually start trying this out in sawmills in actual production. We have expressed the hope that this kind of data that we are using and the models we are using here can benefit both the forest enterprises and also the sawmills, so that we can grow together in this value chain. And yeah, especially what Johannes told us at the end is, okay, there's even more that we can do. So partly it only depends on computing power, so that we have actually the speed and the power to do the calculations, so that we look into the future and say, okay, and as computing power increases, we can get even better predictions and even better models.